Welcome to this explainer. You've probably seen the headlines, right? Earth is heating up. But there is a really fascinating and frankly critical mystery that's capturing the attention of scientists right now. Recent observations are showing that our planet is actually warming much faster than many earlier projections anticipated. So why is reality outpacing the forecast? Let's dive in and find out.
Here is our investigation dossier for today. We're going to systematically break down the data to understand this gap between prediction and reality. We'll be looking at the climate prediction mystery, how climate models actually work, what real-world evidence shows, why warming is accelerating, the stakes for our future, and finally, whether we can still change course. Okay, let's get into it.
Section 1. The Climate Prediction Mystery. Over the last few years, a growing body of scientific observations has revealed something absolutely crucial. Our climate system is responding at the very upper end of our scientific uncertainty ranges.
Which naturally leads to a massive question. Are climate models just flat out wrong? I mean, it's a completely fair thing to ask when reality seems to be lapping the forecast, right? But the scientific answer is a bit more nuanced. The underlying physics aren't wrong. Rather, the real-world climate system is responding at the absolute upper bounds and sometimes even beyond what those models originally expected.
Section 2. How climate models actually work. To solve this mystery, we first need to understand our baseline. These models aren't just taking random shots in the dark. They're highly complex computer simulations representing the Earth's atmosphere, oceans, land, and ice. And they're built on firmly established physical laws like thermodynamics and fluid dynamics.
Now, it's fascinating to look at what actually goes into these simulations. They aren't magical crystal balls predicting one exact future. Think of them more as scenario generators. They rely on incredibly specific human and physical assumptions, like what future greenhouse gas emissions will look like, population growth, industrial activity, energy consumption patterns, and physical mechanisms like climate sensitivity and feedback loops. The IPCC uses these exact inputs to produce a range of possible warming pathways.
So the crucial point is this. Climate models do not give us exact trajectories. They give us probability scenarios with ranges of uncertainty. They basically say, if humanity does X, the climate will likely do Y. Right now, the real-world outcomes aren't breaking the laws of physics, they're just falling at the absolute high end of those probability scenarios.
Section 3. What real-world evidence shows. Let's shift away from the computer simulations for a second and look at the actual observational data coming in right now from satellites, ocean buoys, and weather stations all over the globe. These surface-level instruments are giving us some vital, undeniably clear clues. We're seeing consistently rising global surface temperatures, with recent years continually breaking all-time records. We're also tracking an increasing frequency of extreme heat, heavy rainfall, and prolonged drought. But perhaps most strikingly, we're seeing Arctic amplification. The Arctic is warming several times faster than the global average, which is a phenomenon way more pronounced than what many earlier model averages had suggested. And this brings us to a frankly staggering number, 90%. More than 90% of the excess heat trapped by greenhouse gases doesn't actually stay in the air. It's absorbed directly by our oceans. Because of their massive thermal capacity, the oceans are the ultimate truth-tellers of planetary heat. And measurements show their heat content is rising at a rapidly accelerating pace.
Section 4. Why warming is accelerating. If the oceans are confirming that the heat is rising faster, we really need to ask why. We're going to examine the specific interacting factors, the culprits behind the scenes, if you will, that are actively pushing our reality toward that upper bound.
The science points to a few primary accelerating factors. First, global greenhouse gas emissions have simply tracked much closer to the high-end scenarios rather than the moderate ones. Second, we're seeing massive surges in methane, which is a highly potent greenhouse gas coming from agriculture and fossil fuel extraction. Third, there's a reduction in aerosol cooling. And finally, our planet's natural carbon sinks are actually weakening.
Let's look a little closer at that third point because it creates a fascinating and highly counterintuitive mini-narrative known as the aerosol paradox. On one hand, air pollution, specifically sulfur compounds, actually reflects sunlight, which creates a temporary cooling effect in the atmosphere. But ironically, as we correctly implement clean air regulations to protect human health and clear up smog, we inadvertently remove that reflective shield. This diminishing cooling effect suddenly reveals more of the underlying greenhouse warming that was already there. It's a stunning example of just how interconnected these systems are.
Then we have our carbon sinks. Historically, our oceans, forests, and soils absorb roughly half of all human carbon dioxide emissions, leaving the other 50% in the atmosphere. But here is the alarming part. Their efficiency isn't constant. Warming oceans naturally absorb less CO2. Deforestation, heat stress, and widespread drought mean our land-based sinks are absorbing less too. They're basically becoming less efficient, which adds even more unchecked pressure to the overall warming system.
This brings us to a really critical concept in climate science: feedback loops. These are interacting mechanisms that can actually amplify warming, pushing the climate system toward faster than linear change. Now, looking at the science neutrally, this doesn't automatically mean we're facing immediate runaway warming, but it is a major acceleration mechanism. Change triggers change. When one thing shifts in the climate, it basically sets off a domino effect.
Take the ice-albedo feedback loop, for example. It's a perfect step-by-step illustration of how one physical change logically cascades into another. Step 1. Rising temperatures melt white, highly reflective ice. Step 2. This exposes the darker ocean or land surface underneath. Step 3. Because darker surfaces absorb more sunlight instead of reflecting it back into space, way more heat is trapped. And Step 4. That newly trapped heat accelerates the overall warming, which then melts more ice, and the whole cycle continually reinforces itself.
Section 5. The stakes for our future. Okay, so we've unraveled the mystery of why reality is outpacing the models, looking at the emissions, the aerosols, and those powerful feedback loops. But what does this acceleration actually mean for the planet if these current trends continue?
Based strictly on the scientific data, the expected outcomes are severe and wide-ranging. Under extreme weather, we can expect more frequent and intense heat waves, floods, and storms. For sea level rise, we're looking at accelerated coastal impacts driven by those melting ice sheets and the thermal expansion of the oceans, literally because water expands as it warms. In terms of food and water, shifting rainfall and temperature changes will significantly reduce agricultural productivity. And finally, tipping points. This is the profound risk of crossing critical thresholds in major forest zones or ice sheets that lead to long-term, irreversible changes. We're talking about massive implications for ecosystems, global infrastructure, and economies.
Section 6. Can we still change course? Because while the data is sobering, it is absolutely crucial to understand that this trajectory is not permanently fixed. The ultimate outcome is still very much tied to the human response.
The scientific consensus shows clear mitigation pathways. Because the climate responds to cumulative emissions, taking action now can still drastically limit the warming trajectory. Rapid emission reductions remain the absolute top priority. Alongside that, specifically targeting methane reduction can yield incredibly fast climate benefits, mainly because methane traps a huge amount of heat but leaves the atmosphere much faster than CO2. We're also tracking a massive global expansion of renewable energy, along with the continued essential development of carbon removal technologies.
I want to emphasize a really powerful quote directly from the source material here. Every fraction of a degree matters. You know, it's easy to think of global warming in whole numbers, but the science emphasizes that preventing even a tenth of a degree of warming significantly reduces the severe risks we just looked at. Delays simply lock in higher risks. So the mystery isn't really a mystery anymore. The gap between climate predictions and reality isn't a contradiction. It's a clear warning that the most critical scenarios are no longer theoretical. They're actively unfolding. The question isn't whether warming is happening faster, but how quickly humanity will respond to the alarm bells. Thank you for joining me on this explainer. Keep questioning, keep learning, and I highly encourage you to dive into the data yourself, because the next chapter of this story is really up to us.